I think what's very exciting is that we have the chance of really discovering new principles about how nature works. In our case, we're focusing our research on understanding how proteins come together in order to generate biological functionality, and what happens if this assembly process goes wrong and results in disease. Another aspect that I particularly enjoy about our research is how interdisciplinary it is. In my research group, we have members with backgrounds from effectively every area of chemistry, and also beyond, for example, biochemistry and physics. It's really wonderful to have such a diverse set of people come together to really try and solve some of the major challenges in modern science and biomedicine. Proteins are the fundamental building blocks of life. My research is concerned with understanding the basic principles that govern their ability to come together to generate function, and what happens if this process fails and incorrect assembly occurs, and how this is linked with the onset and development of disease. In order to do our research, we often develop new tools to be able to study and probe phenomena which have remained inaccessible so far. One of the areas we're particularly excited about is the ability to be able to probe proteins on the scale of a single cell. We do this by using microfluidic devices, which are increasingly opening a completely new window into molecular behavior. Our research is concerned with understanding normal protein assembly, how this leads to function, but also understanding how this process can fail and lead to pathological assemblies. It turns out that incorrect assembly of proteins is connected with over 50 increasingly prevalent and currently incurable disorders such as Alzheimer's disease. Unfortunately, these diseases are increasingly prevalent, and the situation is such that almost all of us have in our family members who are affected by these diseases. One of the reasons why it has been so challenging to do anything about the situation is because of the difficulty to be able to probe the fundamental molecular mechanisms by which proteins misassemble. And this is something that we have had the chance to be able to change over the past few years, and we're incredibly excited about the opportunities now to really study aberrant protein behavior at the single molecule level. One of the aspects of our work that I'm particularly excited is our work on bringing physical chemistry concepts into the field of protein aggregation, in particular through mechanistic studies. We've had the chance to extend the formalism of chemical kinetics to be able to deal with protein aggregation phenomena. This has really opened up a window into the mechanistic features of protein aggregation. We work both on functional protein assembly, understanding the basic principles that govern the interactions between proteins and how we can use this to generate new types of useful materials out of naturally occurring proteins for functional purposes. We're also very interested in understanding how and why this process can fail, and how this can lead to the formation of pathological structures which are involved in disease. We're particularly interested in trying to understand the natural defense mechanisms in place in our bodies which prevent this aberrant association for the vast majority of our lives. In particular, for example, natural chaperones. And we've spent a lot of time over the past few years trying to understand how they work and keep us healthy. We're now increasingly taking inspiration from these natural molecules in order to design artificial therapeutic molecules which can act when our natural defense mechanisms decrease in efficiency as we age. Personally, I think it's important for us to work on really fundamentally new science, which is curiosity driven. We discover new principles. I think it's also, personally, I feel it's important that we contribute to solving some of the major societal problems, in our case, understanding the molecular origins of dementia. As a scientist, I'm always very happy to talk about science and technical aspects, but one of the great things about Cambridge is that there's an opportunity to engage with a much sort of broader set of stakeholders. So we interact a lot with clinicians and also patient groups, but also sort of venture capital funders. And that's certainly, from a personal point of view, been a learning curve, but I think it's a very useful experience, and Cambridge offers a fantastic environment in order to be able to build those kind of skills. One of the best parts of the job is really the chance to work with a fantastic set of hugely talented students and postdocs from very diverse backgrounds. And one of the things I'm very proud of is the fact that many of these people have already gone on to have fantastic careers, either as professors in leading universities, or have even helped to found companies to take some of the technology out of the university into the real world.